Hello folks, I have already done 3 video segments, tutorials 1, 2, and 3 in this playlist where I discussed the concept of interference fit for an example. But there's something that is left out and I would like to bring your attention to it. And that is the interference fit icon in the 3D experience is called contact interference, and it's right there. Okay. What I want to show you is it really needed to use this in order to simulate an interference fit or contact fit or pressure fit in a problem? Okay. Now, in the tutorials 1 through 3, I have actually done it with this icon, but we would like to look at that thing more closely. Incidentally, these are all meant to be the same thing. Okay, so depending on the software or the paper or the textbook that you use, yeah, one of these may have been used, but they are all meant to be the same thing. So I'll do that in the context of this simple example. There is a follow-up to this tutorial 4, namely tutorial 5, which I do something else to this problem. But right now, let's not worry about that. So we have two pieces. There is this green piece, which is made out of steel. We call it a shaft. And there is this disc here. There is a disc which has of course, a hole in it. And the radius of the hole is a little bit smaller than the radius of this shaft. And therefore, somehow you want to press fit this or shrink fit this disc into that shaft. So what people do is they heat up, for example, the disc, make it expand, so the radius becomes bigger than the radius of the shaft, and then they slide this thing in and then let it cool down. That's really the whole concept behind this contact interference or press fit or pressure fit. So this is drawn, these are all symmetric models, so they're all shown here. Notice that the, the, the radius of the shaft, this is the shaft, is 20.5 millimeters, whereas the radius of the disc is right here. Radius of the disc is actually 20 millimeter. So the hole in the disc is actually a little bit smaller than the shaft radius. Okay, so what I'm going to do in this problem, I will actually model this thing so that it's easy to see what's going on at a distance of 25 millimeter from that end. In other words, this is not entirely laid against that shaft, the end of the shaft, but 25 millimeters away. Now, for the disk, when I create it, I will also create a reference point, okay, and that reference point basically allows me to specify uh, uh, any restraint that I want on the disk. So I will create a reference point here, although the location of it is not important, but I will do it at the center of that hole. Oops. Okay, so both of these are going to be shelled. Both of these are going to be meshed with the tetrahedral element, linear tetrahedral element. Although you might say that, can I use a hex element? Yes, you can, but then you have to do a little bit of partitioning and things like that. And really, that is not the purpose of this tutorial. So what I want to do is do this problem two ways. One is use the we're going to come back to that later on. Use this thing with no contact interference icon used and look at the, for example, one meter stress distribution in the assembly, and then repeat that with actually contact interference used, and you'll see that the results are not that much different. In fact, these are very close. This is 7,000, this is 6,990 or something like that. So I want to show that um, it is not essential to use this contact interference. However, obviously for this problem it's not, but there may be problems where If you just tried it based on uh, without using the contact interference icon, it may take longer, it may be less efficient, but for simple problem like that, it doesn't matter. And that's the purpose of this tutorial, which I'm going to do. All right, so let's go ahead and here is our 3D Experience interface, release 2023. And I have created an assembly. I'm going to insert my first part, which is going to be the shaft. So right click, insert 3D part, and that's going to be my shaft. And the dimensions of that shaft or yeah, the dimensions of that shaft are given here. Okay, so let me go ahead and use these dimensions to make the shaft. So on that vertical plane, I will sketch. Actually, let me get in there. I got into the 3D shape. Okay, so on that vertical plane, I will sketch something that looks like that shaft, cross section of that shaft. So let me make a profile like so. We're going to clean up the dimensions in a minute. Okay, and because I don't want to close this thing and I want to revolve it, so let me make an axis system here. So here's an axis, so I draw a line here. This is going to be my axis. So this is going to get revolved about that axis. Good. Now let's put some dimensions. So this height, is 50 millimeter, and this is 10 millimeter. Okay, and this height is 20.5, about half a millimeter bigger than the disc, as you will see. And well, why don't I make this whole thing, this length from here to here, about maybe 60. See, that really doesn't matter. Actually, let me make it 80. It really doesn't matter. Okay, so that takes care of my my shaft. So exit, okay, and then revolve it. Uh, where am I here? Model preparation. No, I want to be in part design. Okay, so now I'm going to do the revolve shaft. Because there was an axis system, this automatically gets revolved about that and 360 degrees. So this is going to be that green shaft. Okay. Now, now let me apply material properties to this. So we go to tools. Let me create something. I'll call it the steel shaft. And that is November 21, 2023. Okay, it's made out of steel. Refresh this. Okay, so right here, I'm going to apply, close that, apply it to this part, green check mark, we just put in the Young's modulus and Poisson ratio. So structural, Abacus multiphysics, mechanical, elasticity, elastic, so that's going to be 200,000 MPa, Poisson ratio 0.3. Okay, good. So let's save this. And then I'm going to make the uh, the uh, the disk. So go all the way to the top, right click, insert, 3D part. This is going to be the disk. So I'm going to double click on it. On that same vertical plane, I will sketch. It's easier for me if I drew this thing here, that cross section of the disk with the proper distance from the end. So let me do that as a rectangle. Okay, now we're going to put some dimensions. So this length is 60. Okay, that is 10. Okay, and the distance from uh, uh, this to that side is 20. Remember, which is a little bit smaller than half a millimeter smaller than the shaft itself. Okay, and I also want this thing to be 25 millimeter from the left edge, although this is not an issue here. From there to there, I want this thing to be 25. That is not an issue. Okay, now because I want to revolve this thing about this axis, let me create an axis here. It doesn't matter, the length of it doesn't matter. As long as you have a line there, it'll do the job. A line means an axis. And then we say, okay, so model shafted, again 360 degrees. There we are. And notice that you can't see this uh, black line here because actually this is bigger. The shaft is bigger than the hole. That's why you can't see that black line. All right, so what you see there is actually that thing. Okay, let's make that out of aluminum. So tools, create a material. I'll call it aluminum or aluminium. Uh, this is November. Aluminum disc, November 21, 2023. Okay, say okay. All right, so aluminum disc, November 21. Okay, so apply. Close that on this guy. And the only difference is the Young's modulus. So we go here. So structural, abacus multiphysics, mechanical, elasticity, elastic, and I'll make this thing 70,000. Same Poisson ratio. 0.3. Okay, good. Let's save this thing. All right. Now, while I'm here, I'm going to make that reference point while I'm on this part. So let me double click on, once again, 3D shape. I am in this part. So let me make a reference point. So essential, here is a point. Why don't I make this thing? There are different ways of doing it. I can make, for example, a circle center. And let me hide this. So I'm going to make it the center of this. Okay. Let me cancel that for a second. Let me do it on the other side. Okay, so just so that it looks pretty much exactly like that. Although that's really irrelevant, but so I'm going to hide this. I'll do it on this side. Now it looks exactly like the location that I had there. So I have a point here, and this point is going to be used as the reference point for applying restraints and things like that. Bring this thing into show mode. Okay, so we're done here. We're going to go mesh this thing. So let's go ahead. So let's go ahead to the structural model creation. This is where the meshing is done. You click on it. Empty FEM model. You click. All right. Now it says there are two parts here. Which ones do you want to participate in this analysis? And obviously I want both of them. You say okay. All right. And click on the mesh. Click on the mesh. Here is the tetrahedral mesh. Let's do the shaft first. You click on it. You select this. These are the same numbers that I had in the slides. You can see that. Same size elements. You can see 5 millimeter size, 100 millimeter sag, and linear. Okay, so mesh it. There we are. We say OK. Let's apply the properties. So click on the properties tab, and okay, so you can scroll all the way down to the right and select it here, or the reason it's not showing in mine because these are pinned. So let me get rid of these, and let me get rid of that, and on the properties, and there we are. Otherwise you have to scroll to the right. That's okay. So we select this thing. The shaft is going to be, I will select the part body, and it's going to be it's made of steel. Let's go ahead and mesh the disc. So on the mesh, once again, tetrahedral mesh. On that, same size. Say OK. And properties, click on properties. There is solid properties, and I select it from the tree. It's easier for me. It's aluminum. Okay, so this is all done. That's it's all meshed. And while I'm here, I'm going to save this. Okay. Now, the rest of the problem is we're going to clamp this side and do the shrink fit. Okay, so let's go ahead here and uh, we go to structural scenario creation. Remember, this is going to be a simple static problem. Therefore, we can live with the structural scenario creation. Otherwise, if it's explicit calculation, you have to go to the mechanism scenario creation. But anyway, this is fine. So there's the model. You say okay, it's structural. Okay. All right. Good. Uh, on the procedures, we do static step. Okay. And for time step, I put down for time. This is a dummy time, of course. Initial time, I'll put down 0.1. Uh, Automatically, the geometric nonlinearity is checked, but it's okay. So we say fine. There. Yeah. Oh, it's right there. It's done. It's created at least. Okay, good. Now what we're going to do, let me hide this stuff here. Right click, visibility manager. I don't want to see my finite element stuff. Okay, just the part. Say fine. All right. This end is clamped. So we go to boundary condition, clamped. Either you can clamp it or you can say all 3 degrees of freedom are fixed. XYZ, translation XYZ. Okay, good. Now, the next thing is to create a, a contact. Now, keep in mind that even if you were trying to do contact interference, you would need a surface-based contact. Okay, so what I'm going to do, I'm not going to use that, but I will create surface-based contact. So we go to interaction. Under, first of all, define the type of contact property, namely friction, friction coefficient of 0.1. Okay, it's good. And now we're going to go do surface-based contact right there, surface-based contact. So for the main surface, I select the surface of the shaft, which is the stiffer basically part. And for the other one, for the secondary, I'm going to select the surface of that hole in the disc. So let me hide this. Okay, there we are. This is the surface of the disc right there. Okay. All right. And then I'm going to do the coupling. Now, unfortunately, coupling is not here. I forgot to do it before, so that's okay, no problem. And so we go to setup. Sorry, we go to the well, we can do it here actually. If I click on this, it'll take me there. So there we are. Under connections, and there is a coupling here. Let me hide these things. I don't want to see the mesh. Okay, good. So coupling. The coupling is going to be done between, first of all, the type of is going to be this surface, and for the support 2 is going to be that point. Okay, and the type that I want is going to be kinematic coupling. All of these checked. Okay, so that slide that you see is actually this. Okay, uh, yeah, we say okay. All right, and now we go back to uh, physics simulation under boundary conditions. Under boundary conditions, notice that I want to say that this coupling point, this coupling reference point, cannot translate in the axial direction and rotate about that axis. So what I'm going to do is go back here under fixed displacement. I select coupling. You can do it from the tree right here. No translation in this direction, which is y, and no rotation about the y-axis. So what you see there is actually this slide, okay? And then we say, okay. Good. So notice that already this has penetrated the shaft. That's and without using the uh, contact interference, all I have is a surface to surface contact, but there's already penetration there. Okay, so let me quickly save this thing. The shaft, by the way, is in hiding, so let me bring it in the front. The shaft. Yeah. Okay. So that's pretty much it. Let's go ahead and run it. So we go to simulate. Let's do a quick model check. I hope that I didn't forget anything. Then we do a simulation check. If there are obvious errors that may pop up here, notice that I did have to fix that point because translation in y and rotation about y, because otherwise it'd be loose there and it just can move as a rigid body. If things don't converge, what I will do then is I go and change the primary and secondary surfaces, and maybe that will help. We'll see. That's going to be fairly straightforward and quick. Yeah, it's done. And now we're going to run it and hope for the best. So under iterations, This is similar to the monitor icon in the advocacy program. You can see the iterations and whether the steps or the increments are reduced, step sizes are reduced, etc. Yeah, see, it's not converging. I can see that this is going to fail here. You can see that it's gonna say yeah, analysis failed due to error. No problem. I'm going to close that. I go back to the interaction. Well, actually, we can do that from the tree. So we go here under uh, interactions, surface to surface, right there. Double click, flip the sides. Say OK, and let's go ahead and run it now because obviously these are going to be OK. So let's just run it, simulate it. Hopefully that will take care of the convergence issue. Notice that here we have not even used this icon. All I did was surface to surface. Oh, one thing I forgot to do in that surface to surface, I forgot to select the proper interaction. Okay, this is fine, but right now it's going to be frictionless, and I don't want that. Okay, I don't want that because it's going to be frictionless. I created the friction coefficient of 0.1, but I never used it. So I'm not going to even look at this. I'm going to close that. It converges, it's fine. And you can see that you get stuff, but that's really not what I want here. I go back there, back to that surface-based contact, surface-based contact. Here, instead of default contact property, I want the contact property that I created, which is right here. There is a friction coefficient involved here. Otherwise, the other one would have been frictionless. So let's go ahead and run it. You can see it's going to be, these are going to be close, very, very, very fast. Of course, it's a simple problem. Okay. All right. So close that. So if you look at the very end, what you see here is the von Mises stress. Okay. And incidentally, you can look at the contact pressure if you want. Let me see that. Contact pressure. Contact pressure is only shown on the shaft, and of course, if you hide the shaft, you can see it on the disc too. So this is on the shaft and the disc. But anyway, there we are. So the moral of the story is that if you look at the, for example, von Mises stress, look at the von Mises stress. Go back here. It's roughly 6,870 MPa. Good. So what I'm gonna do now is I go back to scenario, okay, and notice that here under interaction I had contact property and structure or surface-based contact. So what I'm saying is that this is what I've done. That's what I've done. And now I'm going to use the contact interference. So let's go here under interaction. I use a contact interference, and from the tree it requires a surface contact, which is going to be the one that I just created, right there, right there. And it's automatic shrink fit. That's fine. Say okay. I've got too many of them. Just let me delete this. Oh, here. Let me delete this. Okay, we have it right there. We can see that right there. Good. And now we're going to go and run it. So what we're doing now, you can see that here you have contact property surface and contact interference, namely this scenario. Okay. Let me update this. Fine. I go to simulate. Uh, these are going to be working fine, but let's go ahead and do it anyway. So it says that nothing to do there. Scenario check. And finally, they're running. So what we're doing now, as soon as we start running, is this situation. The reason these numbers are a little bit off or different from what I had was because I used probably a different mesh layer, but that's fine. Okay, this is pretty much done. And of course, now I have to run it. That was just a check. If I'm not mistaken, the other maximum one misses was 600, 870. Yeah. Iteration, let's check the iterations. Oh, this doesn't look very good. Obviously, it's going to fail here. Yeah. Okay. Before I do anything else, what I'm going to do is I'm going to flip that direction. Let's see what happens then. Run it. It's looking fine now. Okay. Let's close this. Yeah. So right there. Now notice that these numbers are pretty much the same as what we had before. Here I've used the contact interference. There I did not. So the question is, do I really have to do this? Well, obviously you can see that in simple problem, no. But in more complicated situation, uh, the algorithm that uses this to resolve that, to resolve that interference is different from the algorithm that it uses without using the contact interference. So yeah, so that's what's going to happen. Uh, so basically, I've shown you that doesn't matter in this problem. So what I want to do in the tutorial 5, I'm going to make sure that this guy, this disc, is against that shaft. So there's also the possibility of uh, that surface penetrating the other one. There's contact between these two, not in this problem though. And then I'm going to apply pressure on this face, okay? And look at the whole thing. That's going to be tutorial 5. And that requires a two-step process. In step 1, I do the shrink fit. In step 2, I apply the pressure on the outside surface of the shaft. Good luck. Oh, by the way, one thing I forgot to mention is that in when you created the coupling and you restrained the reference point, down here I said no rotations, okay, to be made. The rotational degrees of freedom are not applicable to solid elements. So even if I did not have this rotation about y on, even if I had it unchecked, this would run and it would produce the same results. And the same thing down here. I'm pretty sure if you uncheck these rotations, it will not make any difference. Okay, so because rotations are not degrees of freedom for the solid element, tetrahedral element or Bragg element, then these are unnecessary. For example, you can uncheck this thing, run it, no problem. Or you can uncheck these three, run it, same thing. All right?